All right, here we go for part two. And big long word problem, so I hope you're not copying this out. That's a waste of your time. Got the note in front of you. Um, I think the hardest part of the optimization problems in chapter three were the ones that we had to make our own functions, and I don't think we're doing a lot of that. We're going to be given the functions, which will have some sort of exponential function in them, or a logarithmic function even, and then have to answer questions. And maybe the challenge is figuring out, do we need the function value itself, or the first derivative, or the second derivative, or what's going on, and that's maybe the challenge. This will feel, I hope, very familiar from what we've done in advanced functions, except for there's an e involved, so don't get too scared about that. A, at what rate is the value of the scooter depreciating the instant Ferd drives it off the dealer's lot? So what are we after? Well, we hear rate, so you should be thinking, okay, rate, that's the first derivative. So let's take the derivative. We want v prime at 0, right? Time equals 0 is when Ferd drives it off the lot. That's what we want. So first of all, let's find v prime at t, which is, it's just a exponential function with a number in front. That's the initial value, 4,000. So I'm going to write that, hang that out front, and then the derivative of e to the negative t to the t over 4 is just that function itself, right? Derivative of the exponential function is the exponential function, but then I got to take the derivative of the inside thing. And this is just, remember, I could think of it as this. This is just the number part, right? The exponent on the t goes down to 0, so it's just the number part. And then I multiply I'm going to tidy this up. Negative a quarter times 4,000 is negative 1,000. E to the exponent negative t over 4. And notice that this makes sense, that the value is always going to be decreasing, right? This is always positive, and the value is always decreasing. So here, v prime at 0 is negative 1,000, and then e to the exponent negative 0 over 4. That's just 1. So the scooter is depreciating at $1,000 per year after time equals 0 years. And trying to save those, having to write those words out again. Dandy, how long will it take for the scooter to depreciate to 1/4 of its initial value? How long will it take the scooter to depreciate to 1/4 of its initial value? I'm going to change color just so we can see what's going on here. So now we want, what are we looking for? How long? We want a t. We want t so that, now is this when he's losing a certain amount of dollars per year? No. We want to know when the scooter is going to be worth $1,000, right? So that v at t equals 1,000. This is just a straightforward advanced functions question here, right? So this is in the original equation, e to the exponent negative t over 4. The value is that, and this is just a straightforward, no derivative necessary, divide both sides by 4,000. How do I solve this, though? Let's go get an advanced function students. Hang on, you guys were all advanced function students, so how do we solve this? Well, we got to get the unknown out of the exponent. We're going to take the log of both sides, but we're not going to take the log of both sides. We're going to take the ln of both sides, because that way I have a function composed with its inverse here. This comes down in front, but the ln of e is just 1. And now this is something that I can put into this I can just put into my calculator, and then I'm going to multiply by negative 4 and then have my answer. This is the exact answer. This is the decimal version. I got it here somewhere. 5.55 years. So after 5.55 years, blah, 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 you write a good sentence. What was part C? Part C says, sketch the function. Well, this isn't too hard. We should be able to get this one. We know the initial value was 4,000, and I'm just going to use the stuff that we know here. Um, it's decreasing always. We knew that, so it's going to be going downhill. Makes sense because it's a exponential decay problem. And after 5.55 years, it was worth 1,000. So that'll give me a little bit of an anchor. And do I have to use my curve sketching algorithm? Not really here because nothing exciting is going to really happen anyway. Notice that as t goes into infinity, this part goes to zero and fairly quickly, which means that makes sense. In the long run, Ferd scooter is going to be worthless. Okay, onwards. Maybe this one's more interesting. Some experiments show that the effectiveness of a television advertisement is this function. Um, Notice I'm going to make a switch on this function, by the way. I don't know if I can. I'm going to blow this up a little bit. Instead of negative t over 10, I'm going to make this, maybe make this negative t over 4. All right, make that, I'm going to make it red here, just so that it fits on our graph better. Okay, negative t over 4. And then it says a commercial block is purchased for up to 30 viewings. How many times watched yields the maximum effectiveness? Sketch the function. Maximum effectiveness. So this is, we want to maximize, so we want required. Again, this is almost like a grass problem, right? Grass is, we could use the grass technique, I suppose. We're given this function, which is nice. We don't have to make our own function. And I did change it a little bit here over 2. Don't like the 2. Don't like the 2 there because you folks are tempted to think of this as a quotient rule problem, and it's not that hard. I'm going to go 2 divided into 5 to make it 0.25 or 2.5, and then make this plus a half TE like this, and so that's a little bit nicer. And what are we required to do here? We just want to maximize this function, right? But for up to 30 viewings, a commercial block is purchased for up to 30 viewings. So notice T can't be negative. Up to 30 viewings. And then now we're good. So analysis, not really any analysis we need to do because analysis was often when we had to come up with our function. So we're going to skip that part. Let's get right to the solution. Solution, we want to maximize this, so we go into our optimization algorithm, right, which is to calculate the derivative and set it equal to 0. So this, taking the derivative of this function, maybe I'll copy it down so I don't have to be going back and forth the way up there. This part disappears, gone. And then this part, it looks like a product rule because I got this first piece. Derivative of the first thing is just a half. Write down the second part plus write down the first part. Derivative of the second part. Now the derivative of this is this, right? Derivative of the exponential function is the exponential function, but then I got to take the derivative of the inside thing as well, which is negative a quarter, again. And then what am I doing next? Oh yeah, I got to set v prime at t equal to 0, and then solve. Now, maybe I should have tidied this up a little bit first. That's a good idea. So I'm going to tidy this up before I set it equal to 0. Or while I set it equal to 0, I'll tidy it up. Notice I'm going to take out this factor, which, by the way, doesn't give me any solutions, so that's not helping me at all. And then I get 1, and that's gone, and then I've got negative t times a quarter, right? Negative 1/4 t. And so there's no solutions for that first factor. But in the second factor, 1 minus 1/4 t equals 0, I'm going to get a solution, I think. Multiply by negative 4, I get t equals 4. So t equals 4 is my spot where the derivative is equal to 0. So is that the maximum? It could be a minimum, right? So how do we handle this early on is now I check out the points, right? So I got 4 seems like a good candidate, but then I also have to check out the endpoints. Well, for t equals 4, I'm gonna pause the video and go to a graphing calculator here so I can get those t values. So here we go on Desmos. I jam that in there and put in my table, which was, well, I should have had 0, not 1. 0 and 30. And so I got 3.2, 2.5, and 2.5. So back in my lesson here, I had 3.2, 2.5, and then a little bit more than 2.5, 2.5 and change. But certainly that's going to be the maximum. Therefore, the max effectiveness occurs after 4 viewings, right? T is 4 is not years, it's viewings. And sketch the function. Oh, here we go again. So actually, I'm going to skip the sketching the function because we just looked at it. And notice that in the long run, it looks like there's a vertical asymptote somewhere. Right, there's that 30 that we talked about earlier. That's going to be at 2.5. Does that make sense? Well, yes, it makes sense, because remember, we said that in the long run, the exponential function wins out over any polynomial functions. That when t gets as t goes closer to infinity, many more watchings, this goes to 0 faster than t goes to infinity. So therefore, e at t goes to not to 0, because there's this 2.5. It goes to 2.5. So then that's the horizontal asymptote is y equals 2.5. And then if you wanted a little sketch, even though we kind of spoiled it a little bit, it went like this by cheating. Well, we never cheated. We used Desmos. 4 was at 3.2 in whatever the effectiveness rating is. All right, that's part 2. Back for part 3 to do the last 2 examples, which I hope they get more interesting, because these ones aren't that interesting.